Hi, everyone. Here is the first problem. Take a look at it, and then we will talk about it together. All right, let's start looking at problem 1, part A. So does anybody have any idea on how to start this one? We want to show that f is 1 to 1.
Assume we have a and a B from the domain such that, well, I guess we need two. So we need an A and a B and a C and a D such that f of AB is equal to f of CD. And then we do some stuffs to show that that means they must be the same thing.
Yes, Alec, that's exactly right. So just writing down what Alec said. Instead of using A, B, C, and D, I'm just going to use A1, B1, and A2, B2. And then, just as he was saying, these are 2 points and they're in A. And what we want to show is that if f of A1, B1 is equal to f of A2, B2, then A1 is equal to A2, and B1 is equal to B2. That is what we want to show. So this is our goal. So whenever you need to show that a function is one-to-one, you want to show that every point in the domain maps to a unique point in the codomain, meaning that 2 points in the domain never map to the same point in the codomain. Another way to say that is that if we have 2 points in the domain, like this point and this point, and they map to the same point in the codomain, then the 2 points must be the same. And so that's what we're going to prove here. So if let's start with the assumption, which is that f of a1 b1 equals f of a2 b2. So what that means is 2 to the a1, 3 to the b1 is equal to 2 to the a2, 3 to the b2. All right. Again, the goal is to show that a1 equals a2 and that b1 equals b2. So what we're going to use here, and I think you guys have discussed this theorem in class, it's the uniqueness of prime factorizations. So if we want to try to use that, we're dealing with prime factors. So whenever you're dealing with prime factors, you want to keep in the back of your mind the prime factorization theorem, which states that every prime factorization is unique. So what that means we'll discuss in a moment, although I think you should have seen that in class. So the first thing that we're going to do is divide by 2 to the a2 and 3 to the b2. So when we divide by 2 to the a2, 3 to the b2, sorry, that's not a square. Let me erase that. Oh boy. Oh, goodness gracious. Sorry. That's a2, sorry. And then this is 3 to the b2. Okay, so when we divide, then we have to do it on both sides. And so doing it on both sides, okay. All right, so then this part, the right-hand side becomes 1. And let's just write 1 a little bit differently. We want to use the fact that prime factorizations are unique. So we're going to write this as 2 to the 0th, 3 to the 0th. And the reason that's useful is because this side here is equal to 2 to the a1 minus a2 times 3 to the b1 minus b2. Okay, so now we have that this thing here is equal to this thing here. And prime factorizations are unique, and 2 and 3 are unique. And this is a prime factorization. And that means that the powers on the left-hand side have to match the powers on the right-hand side. So that means that a1 minus a2 is 0, and b1 minus b2 is 0. And so we would conclude that exactly what we wanted to conclude, which is that a1 equals a2 and that b1 equals b2. So that's part A. We've just shown that f is 1-to-1. Are there any confusions about part A? All right, so I guess the lesson from that one, I'm going to have to erase this. The lesson from that one is that when you're dealing with factorizations, and keep in mind that you might have to use the uniqueness of a prime factorization. So that may come up again. So just keep that in mind when you have factorization problems. Okay, so the next part is part B, and I'm just going to erase this, clear this. Okay, so all right, for this part, we want to show that f is onto. So does anybody have in mind how to get started with that?
You pick a B and B such that there exists an A and a B in A, such that f of AB is the B in B that we picked, and then we demonstrate that then we demonstrate that there exists. Let me start over. We pick a B in B, the codomain, and then we demonstrate that there necessarily must be an A and a B in the domain that map to that.
Yes, that's exactly right. And I'll you pretty much had it exactly right. I'll just use a different lettering so that the notation is clear. So as he said, we're going to take a C in the codomain. The codomain is this capital B. So let's let C be in the codomain. That means now that C is a positive factor of 144. So what we want to show, as Alec was saying, is that there exists in AB in capital A such that f of AB equals C. Okay. So to do that, it says that we should use this hint. So we'll try to do that. So C is a positive factor of 144. And 144 is equal to, it tells us that 144 is equal to 2 to the 4th times 3 squared. So we're going to have to use another fact from, I guess, elementary number theory, which is that because 144 has this prime factorization and C is a positive factor of 144, this together implies, and this is just this is a number theory result that we're using, that C is equal to 2 to the x times 2 to the y, where y, whoops, sorry, that's not a 2, that's a 3. 2 to the x times 2 to the y, or times 3 to the y, where y is, so y is a factor of 3, and C is a positive factor of 144, which has a 3 squared. So the factor of 3 that we're going to observe is 0, 1. It's in 0, 1, 2. And the factor, the number of 2's that we're going to observe is going to be less than or equal to 4. In particular, x is going to be in 0, 1, 2, 3, 4. So we didn't actually prove this. So all we did was we said, well, 144 has this factorization, this prime factorization, and C is a positive factor of 144, and therefore C has the factors of 144, but in smaller number. And that's something we didn't prove. We're using that, and that is a number theory result. It's probably not that difficult to show. Intuitively, it seems true, but so we're just using that here. So basically, we're done now because xy is in A. xy is in A because x is in the first part of the cross product and y is in the second part of the cross product. So we've just shown that for every c that is a positive factor of 144, in other words, for every c and b, there exists a pair in A such that f of that pair is equal to c. Are there any questions about part B?
Can we use that number theory result you talked about in on a test directly?
Let's see. James, what is your thought on that? James will know better than myself.
Yeah, no, that should be fine to use that result. Because you're just using facts about like the prime factorization to kind of derive that result. So that'd be fine to use.
Thanks.
All right. So then let's do part C. Yeah, erase this.
We conclude they're the same.
Oh, yes, that's right. Yes. So Alec, yes, he said the answer, which is that, well, okay, we don't conclude that they're the same. We conclude that they have the same size. So, so yes. So for every, so let's focus on part A first. What we have is a bijection, which I think you've probably heard that term in class. So, but the first thing is that F is 1-to-1. So that means that for every element in A, we found a unique element in B. There may exist more elements in B, but for every element in A, we found a unique, distinct element in B. And so from A, we conclude that the cardinality of A is less than or equal to the cardinality of B. And then from part B, we know that F is onto. So that means that for every element in B, we found a corresponding element in A. So there may be more, just based on this fact alone, there could be more elements in A than there are in B, but we know that for every element in A, there is a element in B. So from this, we would have that the cardinality of B is less than or equal to the cardinality of A. And I mean, and from both of these things together, then we have that the cardinalities of the two sets are the same. What we just went through is, that's just intuition. The more important thing I think to remember here is that if you have a bijection between two sets, then the cardinalities of the sets are the same. Because later on we'll be thinking about, or I'm not sure in this class, but generally some of these sets could be infinite, and then it's a little bit hard to reason about the exact number of elements in each set. So it may be, it's good to remember that if you have a bijection between two sets, we say their cardinalities are the same. So, all right. Okay, so let's move on to this one. So take a couple minutes and then we'll discuss. All right. Before we start this one, I just want to say one more thing about this one really quickly. That we showed that there was a bijection, a one-to-one and onto function between A and B. And what that means is that for every element in A, there is exactly one element in B, and for every element in B, there is exactly one corresponding element in A. So there is a there's no, I'm not sure if I can give a better explanation. That's fine. Yeah, we showed it was a one-to-one and onto function, and for those functions, the cardinality is the same, basically because there's a one-to-one and onto correspondence between every element in A and every element in B. So I'll just leave it at that. I don't want to confuse you more, so that's fine. This one, part A, reflexivity. Is it reflexive? Does anybody want to, does anyone know, is it reflexive?
No.
That's right. And why not?
Because a letter never immediately precedes itself.
Yep.
In alphabetical order.
Yep, that's exactly right. So as Alec points out, so for a relation to be reflexive, then every element in A should satisfy that it is related to itself. And what that would mean here is that every letter in the alphabet precedes itself, which is definitely not true. Okay, the next one, is R1 irreflexive? So before we do this one, just irreflexive means that in every element that is in A is not related to itself. So is it irreflexive? I'll just write down the definition while you think about it until someone decides they'd like to answer. So irreflexive, R1 is irreflexive, if for all A in A, A is not related to A. So is R1 irreflexive? Okay, so it is irreflexive because no number precedes or no letter precedes itself, so it's irreflexive. Right. So no letter is related to itself because no letter precedes itself. Therefore, it's irreflexive. All right. The next one is it's transitive. So, yes, is it transitive? Open the chat. Oops. Oops. So is it transitive? Does anybody have any thoughts? Okay, so so that's right. Oh, okay. So it is not transitive, and the reason is because A is related to B. So let me write that out. A is related to B and B is related to C. So A precedes B. A precedes B, so therefore A is related to B. And B precedes C, so B is related to C. But in order for this relation to be transitive, this would have to imply that A would be related to C. But that is not the case because A does not immediately precede C. So on this one, on part A, the relation is immediately precedes. So in the first case with reflexivity, we said that that's not true because a number does or a letter does not immediately precede itself. It was irreflexive because no letter immediately precedes itself, and it's not transitive because A immediately precedes B, so A and B are related. B immediately precedes C, so B and C are related. But this is not true. This is untrue because A does not immediately precede C. All right, so it's not transitive. So then the next one, is it antisymmetric? So while you think about that, I'll just write down the definition. It would be antisymmetric if, and if someone wants to interrupt me and just say what they think the answer is, just go right ahead. I'll just write out the definition here while you guys are thinking about it. So for all, if it was antisymmetric for all A and B in A, we would have the following. If A was related to B, that and B was related to A, that would imply, that would imply that A equals B. And there is a comment in the chat which says, okay. Yes, so someone did say the answer in the private chat that they said it was anti-symmetric. So this one is tricky. The issue is that it is anti-symmetric because this implication never holds. So the antecedent in this implication is never true, so the statement is trivially true. Because a letter, so if A is R1 related to B, that means that A immediately precedes B. But if A immediately precedes B, then it's not true that B immediately precedes A. So it is this antecedent is never true. So that means that this implication is trivially true because the antecedent is never true. So that means that this is an anti-symmetric relation. Okay, so then we can look at B. Are there any questions on the reflexivity, irreflexivity, transitivity, or anti-symmetricness of R1? Was there any confusion about any of those? All right. Okay, so R2, is R2 reflexive? And anyone can shout it out. Okay, so it's not reflexive. The reason is because a letter does not, again, a letter doesn't precede itself. This time it's not immediate precedence that we're concerned with, it's just preceding in any form, but that doesn't, a letter does not precede itself. Okay, part B, is it irreflexive? Okay, thank you, Andrew. So yes, it is irreflexive because no letter is related to itself because no letter precedes itself. Right. Is it transitive? Yes. Yes, it is. So there was a message in the private chat. Someone says, yes, it is. So, and the reason, the reason is because if A precedes B and B precedes C, then A precedes C. So therefore A is R2 related to C. So it is transitive. And then is it anti-symmetric? That's the last one. Yes, it is. For the same reason that R1 was anti-symmetric, R2 is anti-symmetric because this antecedent is trivially true because a letter never precedes itself. Okay, let's move on to the next one. And if there are any lingering questions, you can always message myself or James in the private chat with a question, or in the public chat if you feel comfortable doing that. So oh, whoops, there we go. Okay, so the next one is this, and all right, take a couple minutes to think about it, and then we'll discuss it. All right. Would anyone like to give part A a try? You could either verbalize, or if you want, you can write on the board. All right, I guess I'll take that as a no. Oh,
I have a thought.
okay.
0 is divisible by 3. So if x and y are the same, x minus y is 0. That's divisible by 3. So every number is related to itself.
Yep. Couldn't have said it better myself. That's it. So, yeah. Let's do part B. And if there are any questions about part A, just let me know. That's part A. So, yeah, part B. Prove that the relation is symmetric. So, I guess I'll do this one. Just writing it out. So let's suppose, so to show it's symmetric, we need to show that if xy is in R, then yx is in R. So for part B, suppose xy is in R. So what that means is that x minus y is divisible by 3. So there exists, a integer k, in Z, such that x minus y is equal to 3 times k. All right. And what we want to show is that yx is in R. So that means we want to show that y minus x is divisible by 3. So, well, y minus x is related to x minus y in that I just take the negative on both sides. So if I take the negative on both sides, then we have y minus x is equal to a negative 3 times k, which we can rewrite as 3 times negative k. And then the integers are closed under multiplication. So negative k is an integer. And so y minus k is divisible by 3. So we conclude that yx is a member of R. So that's part B. And then part C, let's do part C as well. I'll just write that one out. So let's suppose, so we want to show that the relation R is transitive. So that means that if x is related to y and y is related to z, then it should be that x is related to z. That's what we want to show. So suppose that x is related to y. And now here x and y are integers. And so implicitly, x and y have been integers in the last proof as well. So if we want to be very, very complete, then we would want to say that x and y are integers, and suppose xy is related. It's kind of implicit that if I said x and y were related, that they were integers, because this relation is defined on z cross c. But so, okay, you don't really need to say that then, that's fine. But whatever. All right, well, okay, x is related to y and y is related to z. Okay, they're all integers because this relation is on integers, so we know they're integers. All right, we want to show that x is related to z. So does anyone have any ideas?
I have an idea.
Okay.
So this is for transitive, right?
Yes.
Okay, so by definition of transitive, we're trying to let's say get three variables A, B, and C. We're trying to relate A and B to B and C. So we could relate in this case for two steps or two cases. The first case being A is X and B is Y, and the second case B is X and C is Y. We try making a system of equations and then equate them together with two different divisible variables.
Okay, yeah. So I think that you have the general idea. You have the right idea. So as he was saying, x is related to y, so that means that x minus y is divisible by 3. So that means that there exists an integer k such that x minus y equals 3k. And also y is related to z. So as he was saying, we need to write out what that means in terms of the relation. In particular, that means that y minus z is equal to 3j for some integer j. And the goal is to relate x to z. So we need to show that x minus z is divisible by 3. X minus z, so now we're going to use a trick. We know that x minus y is divisible by 3 and y minus z is divisible by 3. Well, here's x and here's z, and they're related by y. So let's add and subtract y. So x minus y plus y minus z. Okay, now the first part is 3k and the second part is 3j. Second part is 3j. And so this whole thing is 3 times k plus j. And the integers are closed under addition. So k plus j is an integer. And so x minus z is divisible by 3. And so x is related to z. So we conclude this all implies that x and z are related. What's up, Mike?
So I have a question regarding if the relation was x plus y, how would we treat that scenario here with x plus y equals 3k and y plus z is equal to 3j?
So basically, so you're saying that the relation is this one instead?
Right. Just where the part is for x minus z equal to x minus y plus y minus z. How would we treat that scenario? Do we just treat the same, add and subtract y?
Okay, so now we're saying that x plus y equals 3k and y plus z equals 3j. And we want to show that that x plus z is a multiple of 3. So this may not be true. We have to think about it a little bit. What this tells us here is that x plus 2y plus z is equal to 3. It's a multiple of 3. So 3p, for the p is just k plus j. So x plus z is equal to 3p minus 2y. Okay, so what we want to know is x plus z a multiple of 3? So if we're not quite sure that it's true, so we need to try to come up with a counterexample. So to see if it's not true. And if we can't come up with the counterexample, then we should try to prove it. So you know, if let's say that somehow we could make p equal to 1, well, p is k plus j, so we're not going to be able to do that. Well, no, we could do it. Okay, x plus c. Is divisible by 3. Y plus c is divisible by 3. Okay. So I'm not. So what we do know is that x minus c is divisible by 3, because if we take the difference of them, then that's divisible by 3. But I'm not so. I think you should be able to come up with a counterexample. So that would be a good exercise. And I mean, we have 2 minutes left, so we don't really have time to do anything else anyway. So let's think more about this. We want to show that if x plus y is divisible by 3 and y plus z is divisible by 3, it's not necessarily the case that x plus z is divisible by 3. So let's set x equal to 2 and z equal to 2 and y equal to 1. So then 2 is not divisible by 3. But y is equal to 1 here. Sorry. Yeah. Sorry. Yes. Okay. So just to set the stage is set here. We have x equal to 2, z equal to 2, and y equal to 1. Then x plus y equals 3. So x plus y is divisible by 3. And y plus z is equal to 3. So y plus z is divisible by 3. And then Mike's question is this relation that x plus y is divisible by 3, is that a transitive relation? And the answer from this example is no, because x plus z is equal to 4, which is not divisible by 3. So that was a good question, Mike, and that's it's good to try to tinker with things and see what you can prove or what you can't prove. So it's 3:45. James has office hours today at 2 p.m. I will stick around for a couple minutes just in case you guys have any additional questions. Other than that, have a great weekend, and if you like basketball, enjoy the tournament.
You have time for me to ask you a homework question?
Yep.
Okay. Let me grab my copy of my homework. So in general, is it possible for a relation to be symmetric and transitive but not reflexive? Because it seems like that's not possible to me.
So that's a good question. If we think it's not possible, then we should try to prove it. So,
here's my verbal proof, not formal, but so if it's symmetric, then A and B is in R implies B and A is in R, right? And then if I sub that into the definition of transitive, that implies that A is related to A.
Done. That's right.
So no, it's not possible for it to be symmetric and transitive, but not reflexive.
Yes, that's what you just proved. If A is related to B and B is related to A, which if A is related to B and B is related to A, then A is related to A. And so You want to know that every, oh, hold on a second. You want to know that every A is related to itself. So you want to show, or sorry, you're trying to show that symmetric and transitive implies that it is reflexive.
Yes.
So you want to know that every element A is related to itself. But what if an element A is not related to any other element? Consider that case. So what happens then? Does your proof still work?
No, I don't think it does.
That's right. Because you needed a B, and now you don't have one. So
Okay, so you're right. So I can't say that it's definitely reflexive, but it is if the relation is total on the domain.
Remind me, what's the definition of total again?
I totally could be using this wrong. I just mean it's like every element of the domain is related to at least one thing.
Okay, well that yes, if that's what total means, then yes, that additional assumption gives us the implies reflexivity in addition to the symmetry and transitivity. Yeah.
Okay.
So we can come up with relations which are not which are symmetric and transitive but not reflexive. But if you add on that additional assumption, which is that every element is related to itself, is related to some other element, then you get the reflexivity.
Gotcha. Okay, that makes sense to me. That makes sense to me. I'm asking this because of problem 11 on the homework. Another side question. So a function composed with its own inverse, and we're assuming it exists, isn't that always the identity function? But then that's not true for relations somehow?
Function composed with its inverse is the identity, yes. With relations, it's a little bit, relations are sets, they're not functions. And so to answer a question about the composition of relations, it's helpful to recall what it means for two relations to be composed. So let me, I think for that question 11, the most important thing is just to remember the definition of what the composition of two relations is. So if the composition of two relations, let's say that A and B are both relations, and then, so A and B are relations. Let's say that they're both that A is a relation on x1 cross y1, and that B is a relation on x2 cross y2, then the relation A composed with B is another relation. And the definition of this relation is it is the set of AC pairs such that it is in x1 cross y2. Oh, whoops, x1 cross y2. Okay. I'm missing something here. So sorry, I just need to erase one little thing. So this needs to be y1. So the thing, well, you can define the composition of relations as long as they have this thing in common, this input in common. So this is in x1 cross y2 such that there exists a B in y1 such that AB is in A, and BC is in B. That's the definition of the composition. Um,
That makes sense. Um, can I ask some more
Yeah.
questions about 11 that are related?
Yeah.
It seems to me that if a relation is symmetric and transitive, then its reverse is itself.
if a relation is symmetric, okay. So the other part of that problem is the definition of its reverse, which is this thing. Is that what you mean?
Yeah, and you just flop the directions, but so like here's my thought process. If it's so let A, B, and R be given.
Mhm.
Definition of symmetric tells us BA is in R as well.
Mhm.
And transitive tells us that AA and BB are both in R as well.
Reflexive or AA and BB?
While transitive combined with symmetric tells us that any element that is related to something else is also related to itself.
Yeah.
So AA and BB are also in R. So then, is there any way I could draw? Could you like erase this so I could draw?
Oh
stuff?
yeah. Yep. I think you should just be able to draw starting. Can you just draw on the screen?
Yeah, can you see that?
Yep.
Okay, so we have man, this is really hard on a trackpad.
Yeah.
We have AB being given, and we showed already that means BA is there, and so is AA. So if I do, and this is R, right? They're all in R. So then if I take the reverse, that means BA, I swap those pairs. AB, I swap those pairs. And AA, I swap those pairs and get the same. And so it seems to me like for any element, any ordered pair in R is also in R reverse.
Yep. And that just comes from the reflexive or the symmetry. A relation is equal to its inverse, provided that the relation is symmetric.
Right. So the question asks us to prove that R is equal to R inverse composed with R.
Mhm.
Why does it ask us to show that instead of just showing that R is equal to R inverse? Like,
Well, wait.
there's some additional insight about relations in general that I'm supposed to be gaining here, or is it did it just add complexity for the purpose of being a harder question?
Okay, so just so I'm verifying, we're trying to show this. I can't remember exactly what the problem said. Is that right?
Yes, that's correct.
Okay. So
But
what
if
you have
that
determined is that
this is itself. These and this are equal. So if A and B is in R and I put in A,
Mhm.
it goes to B, which comes into here, and because of the symmetry, goes back to A. But also because of the reflexivity, also initially went back to A and went to B. Because you need this part for this to be true. R equals R inverse dot R.
well, you want to make sure that you're using a set containment proof, because these relations are sets. So I mean, we're not really, it seems like you have all the main ideas here that you need to do the proof, but I mean, what we want you to gain a concept of is what these definitions mean. So that's why we made it more difficult.
I did the proof the way, like, element wise, showing that R is a subset and vice versa.
Mm-hmm.
How they've told us to do it in the past. But I was just wondering why the question isn't just prove R equals R inverse, because both of those are true, right? Like, and that's what I'm trying to find out is, am I missing something such that this isn't necessarily the case?
No, no, you're not missing anything. This is equal to R, so this ends up being R composed with R, and then based on what we have, that's equal to R, and this whole thing is and R is equal to R inverse. So all of these things end up being equal here. So we just wanted to make sure that that the students are starting to gain a grasp of the composition of relation definition.
Okay. Cool. Well, that was all. I just wanted to see if there was an insight I was missing.
Nope, that's all. Yep, I'm impressed with your work in the course.
Thanks. I really enjoy it. It's fun. It's I like this more abstract math.
Yes,
I dislike arithmetic. I like this stuff with only letters and symbols and all that. Also, my mom is a discrete math professor at UCSC. So it's like, you know,
Santa Clara.
Santa Cruz,
Oh,
UC Santa
Cool.
Cruz. She teaches a discrete math course that's split. They're on the quarter system and it's split into 2 quarters. So her class is essentially the first half of this one. So we're past the point that she teaches. But anyway, I was just mentioning that as a fun fact.
that's cool. Well, there's plenty of math courses at the University of Utah to take. So most of them are in the math department, but
Unfortunately, I am not going to have much room for more math for my schedule because I am a junior and I have, once I finish linear algebra, which I'm in right now, I need one more math course